we've got our translation operator. Let's see how we can use it. And we'll use it to define the coherent states. So here comes the definition of what a coherent state is. It's a beginning definition or working definition until we understand it enough that we can generalize it. By the time we finish the lecture, this definition will be generalized in a very nice way, in a very elegant way. So coherent states. So here it goes. I'm going to take the vacuum state of the harmonic oscillator, the ground state of the harmonic oscillator, and simply displace it with a translation operator by x0. So this is going to be e to the minus I p hat x0 over h bar 0. And I want a name for this state, and that's the worst part of it. There's no great name for it. All notations are not, I don't know of any notation that is very good. If it's very good, it's cumbersome. So I'll write it like this. A little misleading. I'll put a tilde over the state. You could say it's a tilde over the x, but it really, morally speaking, is a tilde over the whole state. It means that this thing, you should read, there's an x0 here used for the translation operator that appears here. So that's the state x tilde 0. Intuitively, you know what it is. You have the harmonic oscillator potential. Here is x. The ground state is some wave function like that. This state has been moved to position x0 and presumably some sort of wave function like that because this translates the wave function. So the ground state, move it up there to the right. That's what it is. That's a coherent state. And there's no time dependence here so far. So this is the state at some instant of time. The coherent state, maybe you call it at time equals 0. Let's leave time frozen for a little while until we understand what this state does. Then we'll put the time back. So a few remarks on this. x0 is how much? Now, don't think these are position eigenstates. That's a possible mistake. That's not a position eigenstate. This is a coherent state. If this would be position eigenstate, you say delta of this minus that, but there's nothing to do with that. Can you tell without doing any computation what is this number? How much should it be? Yes. It should be 1. Why? Because it's a unitary operator acting on this thing, so it preserves length, so this should be equal to 0, 0 should be 1. Very good. No need to do the computation. It's just 1. Psi associated to this state is the ground state wave function at x minus x0, where this refers to the wave function x0 is psi 0 of x. So this is what I was saying here. The wave function has been translated to x0. The remark over there. So these are our coherent states, and we want to understand the first few basic things about them. So we can do the following simple computations. So if I have to do the following, if I have to compute the expectation value of any operator A on a coherent state, I use the fact that I want to go back to the vacuum, so I put Tx0 dagger A, Tx0, 0. Because that way I trace back to what the vacuum is doing. It's much easier to do that than to try to calculate something from scratch. So for example, we have here that x naught, x naught, well, you would replace it by t xt, t dagger xt, which you know is x hat plus x naught. We calculated it a few seconds ago. Top blackboard. And therefore, you got, what is the expectation value of x on the ground state? Is 0, very good. And therefore, we just got x0, which is what you would expect. The expectation value of x on the coherent state is x0. You're there. You've been displaced. How about the momentum? x0, p hat, x0. Well, p acted by the translation operator is unchanged. Therefore, we got 0, p, 0, and again that's 0. So this state still has no momentum. It represents a t equals 0, a state that is over here. And just by looking at it, it's just sitting there, has no momentum whatsoever. Another question that is interesting, what is the expectation value of the Hamiltonian on the coherent state? Well, there should be, now you imagine in your head, t dagger h t. Now, h is p squared over 2m, and that p squared over 2m gets unchanged. P squared over 2m is not changed because t dagger and t does nothing to it. T dagger from the left, t. Nevertheless, the Hamiltonian has a 1/2 m omega squared x hat. And x hat is changed by becoming x hat plus x0. Well, we don't want to compute too hard, too much effort here. So first, we realize that here's the p squared over 2m, and here's the m omega squared x hat squared. So that's the whole Hamiltonian. So we got 0, h, 0, plus the terms that, extra terms that come here. But what terms come here? There's a product of an x naught and an x between 0 and 0. X naught is a number, so you have an x between 0 and 0, and that's 0. So the cross product here won't contribute to the expectation value. So the last term that is there is the 1/2 m is a number, omega squared, x0 squared. And what is the expectation value of the Hamiltonian on the vacuum is h omega over 2 plus 1/2 m omega squared x0 squared. And you start seeing classical behavior. The expectation value of the energy at this point is a little quantum thing plus the whole cost of stretching something all the way to x0. So 1/2 of k squared, k for the oscillator, x0 squared. So the energy of this thing is quite reasonably approximated, if x0 is large enough, by the second term. And this is the cost of energy of having a particle off the potential. So it's behaving in a reasonable way. You can do a couple more of little exercises that I'll put here as things for you to check. Exercise. x0 tilde x squared, x0 tilde. Just calculate, it's just useful to have x0 squared plus h bar over 2m omega, and x0 tilde p squared x0 tilde is m h omega over 2. And finally, x0 tilde xp plus px, x0 tilde is equal to 0.